right, so today we are going to see lab 5 for multisim part, uh, the pre-lab portions, part D. So it's a multisims like function generator and then scope, so instrument, blah, blah, blah. All right, so I'm going to show you for the live versions. I believe the desktop versions I already have examples on the D2L, so you can view that. But if you are using desktop, if you're using live versions, feel free to view these videos. Okay, so first of all, you go to the source and click the AC voltage. All right, so you got AC voltage here. Okay, the peak voltage, so go back to the lab and you read carefully. So it's a with a peak voltage of 5 volts. All right, so it's 5 volts. We change this number to 5 volts. Now let's see the frequency is a 1000 hertz. All right, the default value for Multisim Live is 1000, so it's 1K. So yeah. Now it says connect function generator output directly to channel 1 input as a scope. All right, so the function generator you are using in the lab internally, there's a 50 ohms resistors, okay? But the function generator we are using on the simulations on the simulation software, it does not have that internal resistors. So what we're going to do is we're going to put a random resistors here. I'm just going to put 1K, all right? So what kind, any value you choose is not going to make a difference because this one we just simply measure the function generator's output result. So it's very straightforward. Just connect like what I did. So adding a 1K, you can do 100 ohm, 50 ohms, 2K. It's not going to make any difference. And don't forget your ground. No, okay, your circuit should look like this for this one, the part D. All right. Next, you go to annotations. Okay. Analysis and annotations. Click the voltage. Okay. Put this one. Okay. Anywhere on branch 1 between the function generator and resistors. Okay. So I'm just going to put it here. Now we have everything done. Then all you have to do is just click running, and then you go to graph. Okay, you can see the function is already running. Pause it, you can see it. All right, you can either zoom in or zoom out. Okay, I usually like to see the full cycles. So from here to this. Okay, so this will be one. Right, you can see it's 1 full cycles. All right. Okay, so next things you're going to check is under here. So on the right portions, it say cursor here, all right? There's a few types, so x-axis, y-axis, and track. So I'd like you to choose track, all right? So now, this is cursor number 1, or I'm going to put at the maximum, where I believe it's a maximum. Okay, and we're going to put cursor number 2 at minimum, all right? So this is your minimum, okay? So you can see one value is 4.9802. So I'm going to write it. So the maximum for table 1 so is 4.98, right? Okay, 02. All right. That's the first part I have. And the other one is minus 4.9788. So minus 4.978, I think. Okay, I can't remember the number. All right. So you have those two numbers, and the peak to peak is say the difference, right? So then you're going to see delta y. So on the delta y part, it's a 9.959. So that's a peak to peak voltage. So you're going to write, so what's the number? 9.959. So 9.959. And peak voltage is just same as Vmax because this is a peak, right? Peak is here. Okay, it could be this one, it could be this one. It doesn't really matter which one you choose. They are all the same. 4.9802. All right. Okay, so period. What is period? This means the wave running for a full cycles means from this point all the way back to here. So I'm sure everyone learned that in high school, right? So you just put here to here. So now from this point gets to here, so that's a full wave. So the full wave, you see delta x here is between the cursor 1 and cursor 2 is 997.81 US. So you're going to put 971.1 US. Well, the question asks you to do in microseconds, so you just have to convert it. Okay, how to convert it is up to you. Frequency just 1 over that numbers. Okay, you just divide this with this number, 997 µs, and you got hertz. Okay, this part I'm pretty sure you can handle it. And VRMS, okay, if you don't know what that is, you just have to Google it. All right. Okay, it's very simple. You will calculate it based on your V peak. Okay, and times that numbers. I think it's better you do it by yourself. All right. Now let's move to the second part. Now let's go to the part D. Oh, sorry, part E. Now, the next figure we have, there is a 3K and 2K resistor. Let's look into the graph. So we will have, so it's this one. So R1 is 3K, R2 is 2K. So what we're going to do it, we're going back to the our circuit. Now we need to another one. We need another one here. Okay, so now let's put this here. Right. Okay, so now, okay, I'm going to delete this for a second. So we're going to change this to 3K. And this one will be 2K. Okay. My label is kind of opposite, right? This one is R1 here, R2 here, but mine is R2 here, R1 here. You know what I mean from this one, right? I'm going to put one voltage source here, so PR1, and the other one you will call this channel 2, okay? So on the scope, you're going to do the same thing. So this will be channel 1, channel 2. When you actually walk into the lab, you will see that, okay? So channel 1, channel 2. Are we going to change anything? So it's 5. So our amplitude is still 5 volts. So see 5 volt, 1000. So it's the same things. We don't have to change anything. Okay, when you look into the sine functions, it says 5 sine 2 pi 1000 t. This is your frequency years. And this is your amplitude. All right. So all you have to do it, everything's good. Then we just click run. Then this time you're going to see on the graph, you will see 2 waveforms. Okay, you will see 2 waveforms, both displayed on the same graph. Okay, there's no phase shift. You can see it when you have the 0 crossings. They crossing at the same point. That means there's no phase shift because there's no capacitor or inductors in your circuit. Now we're going to complete the second table. The second table is asking you to calculate VA and VBs. So it's pretty straightforward. You need to know which one is A, which one is B. A obviously is the higher one, B is the lower one. So what you can do, you're using track, but this time you can see on the cursor tool, I'm going to check the second waveform, the blue waveforms, which is your VB, okay? So now I'm just going to put them on the same part, okay? So you can see cursor 1 is at 4.979. 4.9749. So I'm going to write 4.979. Okay, volt. Okay, VB is this one. Here's okay, the blue one is 1.988. There's 1.988. Okay, VR1 is just you subtract this, so it will be 4.979. Okay, minus 1.988. Okay, you can calculate by yourself. Please do it by yourself. And VB is just 1.988. Okay, please do it by yourself and you can know what is it. And the frequency, I'm not going to remind you how to do it. This you can do it by yourself. All right, so we done this part. Now let's move to the very last part. The very last portion is the capacitor circuit, right? So let's take a look. Okay, so part C. Also, you'll have to draw it. All right, so from the above, so sketch the clearly labeled waveform. So you're just going to draw this. Okay, you're going to draw it. Okay, this on here. All right, and it say just be careful. It does say 1 volt per deviations. Means every single block is 1 volt. So for this case, my graph here is not. It's also 1 volt per deviation. So you're going to draw like that. Okay, exactly like how it's on the MultisimLIVE. All right, and you're going to separate, you're going to draw VA, which is the green part, and then VB, which is the blue part here, okay? It's straightforward. Now, let's move to the last one. So you're going to have a RC circuit. Let's go back to here. We will have a 2K and 0.1 mu F. All right, so let's go back to the things. Okay, I'm going to delete this. We don't need that. Okay, let's go to the source. No, actually not the source. We go to the passive. Okay, go to capacitors. All right. Okay, just rotate it. Okay, so we're going to go this way. Okay, complete our circuit right here. The resistor is 2K, so on top will be 2K. We're going back to 2K. And this one, the capacitor is 0.1. So we're going to decrease it to 0.1 UF. All right. The function generator part, we're going to see it. FG's part, does it say anything? Okay, so we have 300s, 1,000, and 10,000. We need to know the, okay. Okay, this one is only asking us to calculate the phase, right? Okay, so on the multisim part, it's actually say 5 volts, so we're still doing the same. And start with frequency 300 hertz. Okay, so start with frequency 300 hertz. So we are not starting with 1K. So this one we're going to put 300 hertz. All right, and this one we can be put here. All right, this one we're going to use calculator to do it. I'm going to show you why we need the calculators. Now let's run it and then go to the graph. Okay, so unlike the previous one, you can see it from the zero crossing point, they are no longer crossing at the same point. So there is a difference. Okay, so there's a difference. What we're going to do it now is you have two cursors, okay, and the question is asking us to calculate the time, the delta t measured on the multisim determined from the delta t in the phase data. Okay, first of all, period. Okay, first of all, period. Period you can use either green or the blue one. It doesn't really matter. So now we're going to find the period. So now I'm moving this to the top, the peak point. Okay, for the blue one, just be careful. You have to keep this in mind. Okay, if you choose blue for one, you choose another blue for another one. Okay, so this one since I'm graphing for let me do the same. All right, so they're both on blue wave. Okay, so I'm going to put this on the top, or you can calculate it from the frequency. It's the same thing. Okay, so you can see one of them is at the blue peak, and the other one is another blue peak. So this the delta t between here and here is your actual period. So the period is minus 3.329 just because I have C1 on the right, so there's a negative. The actual value is 3.332 now. Okay, so 3.329, I'm going to write it here. So now let's go to here. So it's going to be 3.329. The unit is very important. Let's look at the unit is ms. Okay, ms. Okay, so don't forget your unit. Now, we're going to see the phase, right? The delta t. Delta t means from your blue peak to your green peak. What's the delta t? Okay, obviously not. Okay, I'm going to change this one back to the green wave. So it's tracking the green wave. Obviously, you're not going to measure between here and here because this is not the delta t. Okay, the delta t is a too close one. So I'm going to move this one to nearby. So you can see two nearby peak is side by side. Now, this is the green peak and this is blue peak. All right. The delta x here is 205.66. So 205, you're going to write 205.66 US. Okay. And that's your delta t. Okay. So be aware. In a textbook, it may tell you to measure the zero crossing. What you can do is you put this here and you put this one here. Okay, it's 192.8. It's very close to each other. Okay, it's up to you which one you choose. Some people teach you using the zero crossing point, and some people teach you using the peak one. It's up to you and your TA how want to proceed this. There's no absolutely answers on these things. If using the zero crossing is 192.8, the value will be very close. Okay. Now, after you have these two values, what we're going to do is we're going to code the calculators. Okay, we're going to code the calculator out. Okay, so you're going to do 2 zeros. Okay, you're going to do so this will be 0. So it's going to be 0.205 divided by 3.329. All right, and times this will be a full period. This is 360. So my phase is 22.188. So this one will be 22.188 degrees. Okay. Okay, I'm going to explain to you how we get this. All right. So the way it is, okay, when you see this, okay, is saying I have this green wave here, and I have this blue wave here. So we try to know the phase difference between this one and this one over here, right? We try to find out the phase. In order to know that, you're going to measure it. You're going to measure the time from here. Okay, sorry, maybe I choose this one here. Okay, choose from the peak. So I'm going to choose the peak. I'm going to measure the time, the period from here to here, which is, this is equal 360 degrees, right? 360 degrees. All right, so this is 360 degrees for the green wave. Just remember, I'm looking at the green wave, okay? So, and at the same time, you're also calculating the period for this time, saying just saying it is 2 microseconds, okay? So from here to here, take 2 microseconds. After you have that information, all right, you're going to do next things is what we just did, okay? Is measure the time between this line, I'm going to use a different color, okay? Between this line to this line, all right? And we need to know the t for this one. So saying t is 0.1 microseconds, okay? And what's the degrees? Simple, you just use ratios, right? So it basically has 0.1 ms divided by degrees, the unknown degree, okay, equal 2 ms divided by 360 degrees. All right, so that's the equation. That's what we just did, okay? If you get it, it's very simple. You just move the unknown up, then you go 2 divided by 360, then something like that, then you get the result. Very simple. Basically using the ratios, right? If you don't get it, just review it. I think the solution is also providing there. I mean, the equation is also being provided above. So it's nothing difficult, very straightforward. You were able to get it. Okay, so any questions, please let me know it. Obviously, if you're using the desktop versions, it's also pretty straightforward. It's also pretty straightforward, and you can get it. Oh, by the way, there's a 1,000 and 10,000 hertz part. So all you have to do is just go back to your circuit and adjust your frequency to 1,000 and 10,000. And that's it. Okay, good luck on your lab. Hope you enjoy it. Thank you for watching.